Hello. Okay, so today we're going to do this slightly differently to save people having to wait for everybody else to log on. Some of you can't log on, of course, because you are having difficulties. I'm going to record, or I have recorded, this one in advance. Now, the other advantages are you can play bits back, you can pause it to go and get yourself a drink, and at some places I will ask you to pause it so that you can try the questions on the screen, and then when you press play you'll get the explanation. That doesn't mean we won't use Teams again. It's useful to be able to hear you, to ask you questions sometimes, but we'll just try a few different things, means we're going to be doing this for a while. So I'm just going to give you an overview of momentum, which I've already asked you to look at briefly. So some of this will be familiar from GCSE, some of it will be new. So let's just start with the simple stuff. Momentum is a property of any object that is moving, essentially. Okay, anything with mass and velocity has momentum. It is a vector, so it does matter what the direction is for momentum. It really matters in your exam questions, because it does not always give the answer you think it's going to when you start to consider changes of momentum. One such example is something hitting a wall and rebounding back, and every time a good proportion of people will get a question like that wrong because they think they know what the change of momentum is, and actually when you work it out mathematically, because it's a vector, it's not the case. More on that later. The equation for momentum is fairly straightforward. It's the mass multiplied by the velocity. Now we use this P symbol for momentum. Unfortunately, I know we also use it for density, we use it for pressure, but that's just the way physics is. Units for that, if you want to test yourself, you can pause this, but I will carry on. The units are going to be the units of mass multiplied by the units of velocity. So we are looking at kilogram meters per second. And that can also be called Newton seconds, because if you look at the base units for everything there and the derived unit for newtons, you can get to Newton seconds. No, that's not working quite as intended. Luckily I didn't want to show you that one anyway, because that was just sort of two trolleys and we were able to work out their momentums. I think you can all manage to multiply a mass and a velocity, so I'm not going to worry too much about that. So in order to change the momentum of an object, okay, we need to apply a force. This is assuming we can't change its mass, of course. What we're going to need to do is change its velocity, and we know that the only way to change the velocity of something is to apply an unbalanced force. Something can remain moving at a constant velocity, of course, without a force, but it cannot change velocity. And so momentum does bring in Newton's, all of Newton's laws to some extent, actually, in our explanation of momentum. So we do talk a lot about the rate of change of momentum, okay, the rate of change, because the rate of change is proportional to the force. Now let me give you an example. If you are moving in a car, the car has momentum because it has both mass and velocity. If you slow down over a fairly long period, a fairly steady slowdown, you don't feel a great deal of force. Okay, you might sort of feel like you're being pulled slightly forwards, but the car will stop without any real damage. If you had a car with the same momentum, you're sitting in it, and you change the momentum very quickly, so you hit a brick wall or something, you feel a very large force. So the amount of force we experience, or the object experiences, is proportional to how quickly you change the momentum, not just how much momentum it has, but how quickly you change it. Excuse me. And this is really Newton's second law, isn't it? F equals ma, which we've already looked at. So there's a silly example there of a tennis player, of course, to push that ball back in the other direction, he needs to exert a force, and that changes the momentum of the ball. So stated mathematically, Newton's second law is as on the screen there. Let me just bring up a few things here before I start clicking and highlighting. So right, this doesn't look much like Newton's second law. Why is that? Well, Newton's second law as we know it is ma. Now acceleration is velocity over time. So all we've done there is sub v over t in for a to give a slightly more in-depth look at Newton's second law. Okay, and what we get when we do that is we now find we've got momentum on the top here over time. So force is, as we said, the rate of change of momentum. The t on the bottom tells us it's a rate of change of the thing on the top. And we can also see how it ties in with F equals ma. And you can read the blurb there in full, but it's basically saying that F equals ma is a case of Newton's second law. That's not always usable, essentially. Sometimes we need to take into account that the mass may change, so we need this more detailed one. And their example of that is a space shuttle, because the mass of a space shuttle decreases very rapidly as it takes off, so we can't ignore the decrease in mass, which is going to have obviously an effect on the momentum. I'll bring my pen back up here. Oh, okay, it seems I can't, so we'll just do it this way. True or false, we're not concerned with. So don't worry about the animations. If you've copied these PowerPoints for yourself, you can go and look at them. I think my iPad doesn't support them too well, but none of them on this are particularly important. There are plenty of decent videos you can watch if you want to see things moving. The principle of conservation of momentum. This is one of the most important things in physics, okay? Momentum is always conserved in any one direction, in any line, if you like, which is why we call it the principle of conservation of linear momentum. You might not phrase it exactly like that, you just should know that it's always conserved. And some of the points where this can be confusing is where we look at things that are colliding, very common questions, two trolleys colliding, two cars colliding, they can bounce off each other, they can stick together. You've probably seen those sort of questions before. And also where things are exploding, where objects fly apart when initially they've been at rest. Just think for a second, maybe by pausing this, how can an object that's just sitting there with no momentum because it's at rest, how can momentum possibly be conserved if that object then explodes? And we've got lots of stuff flying in all directions where we initially had no momentum. How is momentum conserved? See if you can figure that one out. There is a collision, a weird one to choose, and there is an explosion. And actually, if you think about the gun example, you might get an answer to what I just asked you. Okay, this is not helpful that none of these are working. I can still cover this though. So on the collisions page here, what we would have had were trolleys. So I will be inventive and try and do this for myself. So we've got two trolleys here on a lab bench or so on, going towards each other. Now, of course, what this slide would show us is what happens to the momentum. The momentum afterwards has to be the same as before. That's what all of these questions are working on. It must be conserved. So let's say both of these trolleys had a mass of 2 kilograms, both of them, okay? And they had different speeds. Let's say this one was 5 meters per second, okay? And this one here was going at 2 meters per second. Apologies, I'm doing this with my fingertips, so it's not looking too good. The momentum of the one on the left then, we're doing mass times velocity, 2 times 5, so we've got 10 there. Now, we could choose that as being the positive direction. Remember, momentum is a vector, and usually left to right would be positive, but it's up to you. And the other trolley there, we said that was 2 as well, and that's only got 2 meters per second, so that's got a momentum of 4 kilogram meters per second. So we've got 10 going towards the right, and we've got 4 going towards the left. So the question might be, what's going to happen after this if these trolleys stick together and continue moving? So what's the total momentum we have before? We've got our 10, take away, because it's a vector, our 4. So our total momentum to start with was 6 kilogram meters per second. Positive direction, because the 10 was the direction we chose as being positive. That's our momentum before the collision. We have to have that much afterwards. If they stick together, we now have a combined mass of 4 kilograms. So we would need to multiply 4 by something to get 6. And what would we multiply 4 by to get 6? You might just want to think about this one for a second and pause the screen. And also, what would that number we're trying to find out, what does that represent? So we know that the combined mass is 4, okay, but we don't know the velocity they're moving with afterwards. So you may want to pause it. Some of you may have already worked it out. Afterwards, if we need 6 kilogram meters per second and our mass is 4, that means that our velocity is 1.5. Okay, so afterwards, the velocity of both of our trolleys would be 1.5, and they would be stuck together like this, moving that way at 1.5 meters per second. So that's a very easy example. It's the sort of thing that's on this animation anyway, just to show you how we might use this idea. Momentum before is the same as momentum afterwards. But you see, if I didn't have the direction there, I'd have got a very different answer, because I would have added my 10 and my 4 together and said, oh, well, before I've got a total momentum of 14. Well, that's not true, because momentum is a vector. For explosions, I asked you earlier to think about this. How can something that starts here, a bomb, let's say a comedy bomb with these sparks coming out the top, if this is going to explode, how on earth is momentum conserved? What momentum have I got before? Nothing, because it has no velocity. It then explodes and bits fly out. What momentum have I got now? Well, actually, nothing again, because for every bit that flies that way, there will be a bit that goes that way. For every bit that goes that way, a bit will go that way. Now, the pieces of the bomb might not be the same size, but the mass multiplied by the velocity of that piece will be balanced by the mass times the velocity of a piece in the opposite direction. So actually, it is conserved. And another example I often ask people to think about is if you were standing anywhere and you jump, you've gone from relative rest to having some motion. How on earth is momentum conserved there? Well, actually, the Earth moves in the opposite direction. I know it sounds silly, but the Earth is huge. So if the equation is mass times velocity and the Earth's mass is really, really big compared to yours, then the velocity is tiny, and actually we can't really perceive it happening, but it does happen. And calculation's not a problem, because we do other work on calculations. Now, elastic and inelastic, this has turned out to be a bit more work for my finger drawing than I intended, but what we mean by elastic and inelastic: elastic is where kinetic energy is conserved. Okay, kinetic energy is conserved. So any collision where the kinetic energy before and afterwards is conserved is elastic. Inelastic is where it's not. So I won't bother writing that on the screen. It's the opposite. It's where kinetic energy is not. Don't get confused between kinetic energy and momentum. Momentum is always conserved, okay? Momentum is always conserved. Kinetic energy is not necessarily. A Newton's cradle, you've seen one of these. You move two balls away from the end and two balls sort of seem to move at the other end when they collide. If you moved one, just one would move out at the other end. It's something that shows conservation of momentum. Actually, it's quite a complicated example if you try to explain it properly. Too complicated for what we want, but it does show that momentum is conserved. So why do they eventually come to rest if energy is conserved and momentum's conserved? Well, we know that energy is transferred to other things. There's friction with the air. There's a certain amount of friction in the point where the balls contact the frame, and so on. Okay, and that's why we get inelastic collisions, because although momentum is conserved, kinetic energy isn't, because that movement energy can generate heat, can generate sound, can generate light in some systems, making most collisions inelastic. And to be honest, all collisions are inelastic. Elastic collisions are really a mathematical ideal that we can use to work things out, because there are some things that are close to being elastic. The collision of gas molecules, for example, it's nearly elastic. And then bigger examples, look at things like snooker balls. If you're being very general, they're sort of elastic. They're clearly not, because we get some sound when the snooker balls hit each other, but they're quite bouncy, for want of a more technical word. We know the equation for kinetic energy, actually, because we've done this in a slightly different order. It's half mv squared. This is just telling us how we can get to that. We'll look at our momentum equation, rearrange to get v as the subject, and if you put v into the equation for, you substitute P over M into the kinetic energy equation in place of V, then you end up with this, and that's just an alternative for kinetic energy, momentum squared over 2 lots of the mass. I've never needed to use that. I have seen it in a few books and on here, but I've not had any particular use for that directly. Fill in the missing words we can definitely deal without. Finally, impulse. I know you will have looked at this in maths. By the way, I know this is very quick, this slideshow, but you can pause this at any point and make notes. You can ask me questions in the comments for the video, or you can email me questions on what I've said, or you can just look at the presentation yourself later if you have a copy. So impulse is the product of force and time. Let's have a look at this a little differently. Impulse, therefore, is the change in momentum. Remember earlier on we said that the force that was experienced was to do with how quickly we changed the momentum. It was the momentum over time. So force equals momentum over time. Let me give myself some space here. If force is equal to the change in momentum over the change in time, then doesn't this mean, if I rearrange it, that the force multiplied by the time is equal to the momentum? That's all this slide is saying. And that particular thing, a change in momentum, is known as impulse. Okay, it's known as impulse. And this is actually the very example I gave earlier, so not too much reason to talk about this. This is just asking you, why does the sort of size of the force vary for these cars? Why do cars get so destroyed nowadays, but people actually seem to survive? Cars used to be really strong. You used to be able to have a crash and hardly anything happened. The problem was the damage was done to you rather than the car. What we do now is we have these impact zones where the car will crumple intentionally to increase the time over which the momentum reduces. Now, the slide that we missed there, by the way, was a slide that was going to tell you that if we have a force against time graph, which you quite often will in this topic, then the area underneath that graph will be the impulse. Okay, so just bear that in mind. Other things, you may get these sort of how science works questions. How else do we increase that time and reduce the force? Things like seatbelts do the same thing. the crumple zones is definitely the big one. And that was just a quick quiz at the end, so we don't need to worry about that one. So thanks for watching. Instructions on what to do now are in the email I sent, and you also have the prep that will be automatically sent back to me that I emailed out yesterday on mechanics. And I will speak to you all next lesson. Thank you for listening. This was good.